have the non-homogeneous linear differential equation for second order, page 106, number 1. Y double prime plus 4y prime plus 5y equals 2ex. Now, to get the complete solution of the equation or the general solution, we use y is equal to yc plus yp. Now, this 2e to the x is a function possessing only a finite number of linearly independent derivatives. Thus, yp can be found by the method of undetermined coefficients. Now, this yc is also known as yh or y homogeneous, which stands for the solution of the homogeneous linear differential equation, thus equating the equation to 0. Now, to get the yc, first we equate this to 0. Y double prime plus 4y prime plus 5y is equal to 0. Now, we assume that y is equal to e to the mx. To get the first derivative, m e to the mx, the second derivative, m squared e to the mx. Now, the results, derivatives for this will be substituted in this equation. Y double prime, which is m squared e to the mx plus 4m e to the mx plus 5 e to the mx is equal to 0. Divide this e to the mx. We get m squared plus 4m plus 5 is equal to 0. Now, this one is called the characteristic equation. This characteristic equation has two roots. m1 is equal to negative 2 plus I, m2 is equal to negative 2 minus I. Now, these roots has the nature which is conjugate complex. M is equal to alpha plus minus beta. Now, this falls in case 3, which has the complete solution of the differential equation y is equal to e to the alpha x c1 cos alpha x plus c2 sin beta x. Now, we substitute, the value for alpha is, by looking this, the alpha is negative 2 while beta is 1. Now, we substitute this value to this. Y is equal to e to the negative 2x c1 cos x plus c2 sin x. This is now the value of the yc, which is the complementary solution. Now, how to get yp? How to get yp? Simply by method of undetermined coefficients. Now, 2e to the x as what I said earlier, it is a finite number of linearly independent derivatives. Thus, we use this method, undetermined coefficients. We assume yp is equal to a to the ex derivative of this, still ae to the ex, second derivative, also ae to the ex. Now, to get the unknown a, substitute y prime p, yp double prime to the given equation, which is y prime plus 4y prime plus 5y is equal to 2e to the x. Now, substituting the value, a to the ex plus 4a to the ex plus 5a ex equals to summation 10a ex equals to ex. Now we have the value of a, which is 1 over 5. Earlier, we assumed that yp is equal to ae to the ex, and the value of a is equal to 1 over 5. Thus, the value of yp is e to the x over 5. Now, the general solution for the given equation, y double prime plus 4y prime plus 5y is equal to 2x, is now e to the negative 2x c1 cos x plus c2 sin x plus e to the ex plus 5. This is the general equation for the given differential equation. The next problem is found in page 111, number 10. This is an example of a Euler differential equation. X cubed y triple prime plus 4x squared y double prime minus 5x y prime minus 15y is equal to x cubed. Now, using the generalization, x to the n d to the n y over d x to the n is equal to d quantity d minus 1 quantity d minus n plus 1 y. To transform the various terms on the left hand side of the given equation, we have d quantity d minus 1 quantity d minus 2y plus 4d quantity d minus 1y minus 5dy minus 15y is equal to 2. E to the x to the 3 equals e to the 3z. From this, by expanding the various operational products and then collecting terms, we find d cubed plus d squared minus 7d minus 15y is equal to e to the 3z. The characteristic equation of this equation is m cubed plus m squared minus 7m is equal minus 15 is equal to 0. Thus, the factors are m minus 3 quantity m squared plus 4m plus 5 is equal to 0. From its roots, we have m1 is equal to 3, m2 is equal to negative 2 plus I, m3 is equal to negative 2 minus I, and we obtain the complementary function, which is c1 e to the 3z plus e to the negative 2z quantity c2 cos z plus c3 sin z. Note that we can't use the method of undetermined coefficients, since yp equals a e to the 3z will not guarantee that there is a value of a, because it will result to 0 equals e to the 3z, which is not possible. By this, using Euler's identity, e to the alpha plus I beta is equal to e to the alpha cos beta plus I e to the alpha sin beta. Input this in this to input this alpha and beta in the y complementary function. C1 cos ln x over x squared plus I sin ln x squared plus C2 cos ln x squared minus I sin ln x squared plus C3 x cubed. Now regrouping the terms. Y is equal to C1 plus C2 cos ln x squared plus I quantity C1 minus C2 sin ln x squared plus C3 x cubed. Now let C1 plus C2 is equal to C1 and I quantity C1 minus C2 is equal to C2. Now we redefine this since these are arbitrary constants. YC is equal to C1 cos ln x plus x squared plus C2 sin ln x squared plus C3 x cubed. Now, why is this so? Since this is a x equals e to the z, or z is equal to ln x, simplifying C1 e to the 3z plus e negative 2z, quantity C2 cos z plus C3 sin z will be equal to the redefined solution, which is this. If we have to simplify this using these equations, we will arrive this complementary function.
Play.
To determine yp, we use variation of parameters. We let y1 is equal to cos ln x over x squared, y2 is equal to sin ln x over x squared, y3 is equal to x cubed. Now we compute the Wronskian matrix of these three, y1, y2, and y3. Now we have w sub m is equal to the absolute of the y1, y2, and y3 and its corresponding first derivatives and second derivatives. Now we input this one, cos ln x over x squared, sin ln x, x squared, and x cubed, and then the derivatives of y1, y2, and y3, and so on. After which we have the answers for the derivatives of the y1, y2, and y3. We have 6 cos ln x over x to the 4th, cos ln x, x squared, minus 2 cos ln x over x cubed minus sin ln x over x cubed, minus cos ln x over x squared plus sin ln x over x squared plus 4 sin ln x over x to the 4th minus cos ln x over x to the 4th, sin ln x over x squared, cos ln x over x cubed minus 2 sin ln x over x cubed minus cos ln x over x squared minus sin ln x over x squared over these two over x squared plus 6 sin ln x over x to the 4th, and then the y3, x cubed, 3x squared, and 6x. Now, computing the Wronskian determinant is equal to 26x to the 4th, and then we divide the dE by leading the terms of coefficient x cubed. So this one, we divide the differential equation to the leading coefficient, which is x cubed. Now we get y triple prime plus 4 over xy double prime minus 15 over x squared y prime minus 15 over x cubed is equal to 1. Now since now the fx is equal to 1, we let f is equal we let f equal to 1, and then let v1, v2, and v3 be these equations. Now, why is it necessary that we must obtain v1, v2, and v3? v1, v2, and v3 are necessary for which these are some of the factors to be used to obtain yp. Now, the Wronskian determinant w1, w2, and w3 are obtained through this. So this w1, the answer is negative cos ln x plus 5 sin ln x, where w1 is the determinant of wm with the first column replaced by 0, 0, and 1. So the first column of w1 is replaced by these integers. Now w2 is negative 5 cos ln x minus sin ln x. Another is the second column is replaced by 0, 0, 1 again. And the last is w3, which has the value of 1 over x5, which was the third column is replaced also by 0, 0, and 1. So by this we can now get the values of since we obtained the values of w1, 2, and 3, we can now obtain the values of v1, v2, and v3. So now the values of the v1 is equivalent to negative 5 over 338 x to the 5th cos ln x plus 6 over 169 x to the 5th sin ln x, while v2 is equal to negative 6 over 169 x to the 5th cos ln x minus 5 over 338 x to the 5th sin ln x. Last is v3, its value is equivalent to ln x over 26. Now we have the values of y1, y2, y3, as well as v1, v2, and v3. So we can now get the value of yp. So the summation of the product of v1, v2, and v3 is equivalent now to 1 over 338x cubed quantity 13 ln x minus 5 is equal now to 1 over 26 x cubed ln x. Now the general solution is this: y is equal to yc plus yp. Yc has the value of c1 cos ln x over x squared plus c2 sin ln x over x squared plus c3 x to the cube, while yp has the value of 1 over 26 x cubed ln x. So this is now the general solution of the given Euler differential equation.